What are the practical applications of Bernoulli's equation? Bernoulli's equation is used for finding the discharge of a fluid in Venturimeter and Orificemeter. Both these devices are used to calculate the discharge of a fluid. So these measure the rate of flow of fluid through a pipe or discharge. Both these are discharge measuring devices. And we have Peter tube. Peter tube also uses the Bernoulli's equation to find the velocity of the fluid flow in a pipe. So these devices make use of the Bernoulli's equations principle of Bernoulli's equation, to calculate the discharge and also to find the velocity of flow in a pipe. So let us see the working of a Venturimeter. You can see that a Venturimeter consists of a converging part and a throat and a long diverging part. So this is it consists of the following parts: a converging part, throat, the middle portion is called the throat. This is called the throat, and this is the converging part. So the length of the diverging part is deliberately kept long because to avoid the losses, a minor loss that is occurring, because if there is a sudden expansion there will be losses due to eddy formation. In order to avoid that, we have a long pipe to avoid the eddy formation. So according to Bernoulli's equation, if you take position 1 and 2, and if there are no losses, if you assume that there are no losses, according to Bernoulli's equation, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Since they are at the same level, you can cancel off Z1 and Z2. And you will get this following equation: P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g. And also you know that A1 V1 is equal to A2 V2. A1 is the area of cross section at position 1 and A2 is the area of cross section at 2. So this is according to the one-dimensional continuity equation. A1 V1 is equal to A2 V2. And this is equal to the discharge Q, which we want to measure. So you can rearrange the equation to get P1 by rho g minus P2 by rho g is equal to V2 square by 2g minus V1 square by 2g. And P1 by rho g minus P2 by rho g is equal to H. That is the head difference. So you can write P1 minus P2 by rho g. That is the head difference, H. And this head difference is equal to, this is found using a U-tube manometer. You can see that a U-tube differential manometer. And formula for finding H is equal to, this X is the difference in mercury level, which you can get from the manometer readings, that into specific gravity of mercury. Usually you are using a mercury here. If that is another fluid, then you need to use the specific gravity of that fluid. So specific gravity of mercury by the specific gravity of the fluid that is flowing through the pipe minus 1. So if it is mercury and water, it will be 13.6 by 1 minus 1, that is 12.6. So this is equal to V2 square by 2g minus V1 square by 2g is equal to H. Now you know that V2 square by 2g minus V1 is equal to, from this equation, A1 V1 is equal to A2 V2. If you substitute V1 is equal to A2 V2 by A1, the whole square by 2g is equal to H. So V2 square by 2g into 1 minus A2 by A1 the whole square is equal to H. We are taking V2 square by 2G outside. So this will be equal to V2 square by 2G into A1 square minus A2 square by A1 square. So V2 you will get V2 is equal to A1 into root of 2GH by A1 square, root of A1 square minus A2 square. So you will get A2 V2 is equal to A1 A2 root of 2GH into root of A1 square minus A2 square. Here A2 V2 is the discharge that we need to measure. So the final equation is discharge Q is equal to A2 V2. This is equal to A1 A2 into root of 2GH by root of A1 square minus A2 square. So this is the theoretical discharge, but the actual discharge will be slightly different. That is, you need to add multiply with another coefficient, that is CD, coefficient of discharge, into A1 A2 root of 2GH by A1 square minus A2 square. This is found, this CD is found experimentally. Usually its value ranges from 0.9 to around 0.9 for a Venturimeter. Coefficient of discharge is 0.9. CD is actually Q actual by Q theoretical. So this can be found using experimentally. This can be determined, value of CD. Now let us see what is an orificemeter. See, orificemeter is also a device used to measure the discharge of a fluid in a pipe. So let us see the construction of a orificemeter. So orificemeter is comparatively simple to construct. You can see that this is a plate, a small hole, a plate inserted in the pipe. So this you can see this is the plate, and with a small hole in the middle of that. Okay. So fluid flows through this small hole. You can see the path here. So the U2 manometer is attached here at position 1 and position 2. This position 2 is slightly closer to this orifice. You can see orifice here. So 2 will be at a small distance from this orifice. So here also you are using a U2 manometer. So instead of a converging part, throat and diverging part, you have a simple plate with a hole in the middle of it. So how it can be used to measure the discharge? Again, we are taking 2 points 1 and 2 and apply Bernoulli's equation. So that is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Since they are at the same level, you can cancel Z1 and Z2. So you will get P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g. And you know that the discharge is equal to A1 V1 is equal to A2 V2. This is one-dimensional continuity equation. And rearranging the above equation, you will get P1 by rho g minus P2 by rho g is equal to V2 square by 2g minus V1 square by 2g from here, from this equation. And P1 by rho g minus P2 by rho g, this is equal to H, and this H is found, there is a head, pressure head is found using a differential manometer. You can measure X from the manometer, and you can use this formula to find H. This is specific gravity of mercury or the fluid that is used in the differential manometer, and this is the specific gravity of the fluid that is flowing in the pipe. If it is water, it is 1, and if it is oil, it is 0.9, something like that. Depends upon the fluid that is flowing in the pipe, minus 1. So you can write V2 square by 2g minus V1 square by 2g is equal to H. and V2 square by 2G minus V1 you will substitute from here. From this equation you will get V1 is equal to A2 V2 by A1 the whole square by 2G. So if you take V2 square by 2G out, you will get V2 square by 2G into 1 minus A2 by A1 the whole square, common bracket, is equal to H. So V2 square by 2G into A1 square minus A2 square by A1 square is equal to H. And you can get V2 from here. V2 is equal to A1 into root of 2GH by root of A1 square minus A2 square. Okay, now we have another coefficient, that is coefficient of contraction, that is equal to area of the orifice, area of the vena contracta by area of the orifice. This A0 is the area of the orifice, that is the area of this orifice in the plate, in the middle of the plate. So A2 is the, actually that is the area of the vena contracta, because when the fluid flows through the pipe, it will form a narrow portion. Okay, so this will be the plate. So this narrow portion, this is called the vena contracta portion. The vena contracta, the small narrow area. So you can get A2 is equal to, that is area at the vena contracta is equal to coefficient of contraction Cc into A0. So if you substitute here, V2 is equal to A1 into root of 2GH by root of A1 square minus A0 square into Cc square. So V2 will be, you can get this equation, V2 is equal to root of 2GH by 1 minus A0 square Cc square by A1 square. You are taking A1 outside, it will be cancelled off. So this is the discharge Q is equal to A2 V2 is equal to A2 into root of 2GH by root of 1 minus A0 square Cc square by A1 square. And if you substitute for A2, we have seen that A2 is equal to A0 into Cc into V2 is equal to A0 into Cc. A2 is equal to A0 into coefficient of contraction into this. So this is equal to A0 into Cc into root of 2GH by root of 1 minus A0 by A1 square into Cc square. And here the coefficient of discharge Cd is equal to coefficient of contraction Cc into root of 1 minus A0 by A1 square by root of 1 minus A0 by A1 square into Cc square. This is found out experimentally, and if you substitute that here, you will get Q is equal to Cd into A0 into root of 2GH by root of 1 minus A0 by A1 the whole square, and finally you will get Cd into A1 A0 into root of 2GH by root of A1 square minus A0 square. So this is the final equation for the orifice meter. So Q is equal to Cd into A1 A0 root of 2GH by A1 square minus A0 square. You note that A0 is the area of the orifice, the plate, the area of the hole. A1 is the normal area of the pipe. And here Cd has got a value of around 0.6. It is not as accurate as that of the Venturimeter. So coefficient of discharge will be 0.6, which is found experimentally.